All right. Hello, everyone, and welcome to a new problem of this amazing chapter, which is going to introduce our technique for arrays and for a lot of coding challenges. You're going to use this a lot in a lot of different contexts, scenarios, a lot of problems, and also real life scenarios. So let's jump into it. The problem is called the longest subarray of some maximum s. And we are given an array of positive integers and another integer s, and we should find the longest subarray of some maximum s. If we take a look at this example, we can see that we have the array nums of length 10 and our maximum sum, the s, equals 11. Now, the answer for this example is 3, 8. So we need to return the start index and the end index of the answer subarray, right? So, for example, here the subarray 3, 8 is 0, 1, 2, 3, starts here, 4, 5, 6, 7, 8. What's its sum? 2 plus 2 plus 1, 5, 5 plus another 5, that's 10, right? So, you can take a look at the array, write it on paper, try to find other subarray of which has a longer length, right? A longer subarray with sum at most 11, and you would find it, right? So let's see how we should approach this kind of challenge. Now, as you know me, I'm a huge fan of brute force approaches. I always think in terms of brute force approaches for the start, and then try to work my way up there and see if I can optimize that brute force, or if of course maybe I should change the whole idea, right? The whole way of solving the problem. So this is what I want you to do. Think about a brute force approach. Try to come up with anything, could be n cubed, n squared, doesn't matter, but some solution at least. Some solution is better than no solution at all, right? So let's see what I'm going to do here. We should find the subarray which has two specific properties, right? First one, sum at most s. Second one, it has to be the longest. And again, we have solved this type of problems. There are hundreds of them. When you have to find the most something, subarray or element or stuff like that, one brute force approach is always to try out each and every one of them, right? So this is what I'm going to do. I'm going to try out each and every subarray from the array nums, and of course, among all of the subarrays, only some of them are going to have the sum at most s, and from those ones, I'm going to select the maximum length one. So our brute force approach consists of a couple of steps here. First one is, of course, we need to try out each and every subarray, right? This right now, you obviously know how to do, because we are not given the length or any other thing. We have to fix each pair of indices, right? I and j, where j is of course the starting, the left endpoint, right? And j is the right endpoint of our subarray. Awesome. Now, this is obviously super simple to do. We have to fix two values. So we are going to have two nested for loops for that. So this is like the first step, right? The second one is that once we have a subarray I and j fixed, we need to know the sum of that subarray. And right now, we know a couple of ways to do that. I'm not going to talk about the brute force approach, so don't worry, we are over that. We can, of course, use partial sums, right? So partial sums is one way of quickly getting the sum of any subarray, ij. Or we can have a second approach which we have used on the on that problem, subarray, maximum sum subarray of length exactly k, right? And what we have done there, if you remember, is that we only needed a variable to hold the sum of each of our subarrays. Obviously, this problem is different, but we can do the variable trick here, and it's even easier than what we did there, right? So the second option, which obviously you should always use, is a variable sum. And why did I say that? Because when you have to choose between these two, what are you going to choose? The one that gives you big O of 1 constant extra memory, it's only a variable, or the one which gives you extra memory of big O of n, right? So be very careful at things like that. Don't just rush and say partial sums. If there is a better approach, trust me, the interviewer is going to be way more happy. So we are going to use a variable sum, and we are going to see in a minute how we will update it for it in order to store the sum of every subarray. And once we have the sum, yeah, I guess it's pretty simple, right? We just check if that sum is less than or equal to s, and we update like our answer variable, which holds the longest length of some subarray of sum at most s, right? So the only two things here are fixing the subarray and having the sum computed. The first one we know. Let's see how we should do that with the variable sum. And for this, I'm going to write the two nested for loops for I and j, and I want to show you how simple it is to always know that sum. All right, here there are our two nested for loops. You're probably wondering why I left so much space here. You're going to find out in a moment. So, as I've said, we are fixing the first index I, which can take, of course, any value from 0, the first index, all the way to the index of the last element, n minus 1, and j, which, of course, has to be greater than or equal to I, right? Because we can have an array that starts here and ends here, right? So also be very careful about this thing. So we are fixing each I and each j, and when we are here inside the second for loop, we basically know the subarray I, j, and we need to know its sum, right? Well, let me show you a trick. Actually, there is a very smart way of computing the sum of some subarray using the fact that when we make these two nested for loops, we are basically computing the sums of each and every subarray, right? So it's not like you get a random query, what's the sum of this subarray, like we did in the partial sums problem. You are computing these sums one after another. That's why I said it's similar to that other problem, because maybe we can find a way to compute the sum of the current subarray ij using the sum of the previous subarray, which of course we've just computed, right? So let's see an example for this to make it clear, right? What's the first value that I will take? 0. Then what's the first value that j will take for I equals 0? Also 0. So first, I and j are both here, right? Of course, what's the sum? The only element which is 3. Let me write the sum here actually, right? So the sum is 3. Awesome. Now, we know the sum of the first subarray to ever take into consideration. What's the next thing that happens here? Well, obviously, we move after we do what we're going to do here. We move to the next value of j, which is going to be 1. So I stays at 0 and j becomes 1. What will happen with the sum? Previously, we had only this element. Now, of course, when j got increased, we have a new element, which we have to take into consideration for the sum, right? So the sum will get increased by the new value. And that's it. On the next step, j becomes, of course, 2. So let's take the j out of here and we'll have j here. how does the sum change? Of course, it's the previous sum that we had on the previous subarray with, of course, the extra element. So the sum from 5 will get increased by 5 and becomes 10. Of course, when j is here, we see the value of nums of j and also increase the sum and it becomes 12, and so on and so forth, right? So it is that simple. If we know the sum of our current subarray, ij, when we move to the next one, so j gets increased, we will just increase the sum by nums of j. And that's all. So technically what I have to do here is just increase the sum variable, right? We'll have a variable for that. And increase it by the new value that we have just added to our subarray. So sum plus equals nums of j. Awesome. Is that it? No. There is one more case, of course. And that case is when we move to the next subarray, we either increase j or maybe let's say I. So I is 0. And after going through each value of j, j is at some point, of course, on the value n-1, so the last iteration from this loop, and we have the sum, which, of course, I don't know, you can compute the sum, it doesn't matter, that's not the point. We have the sum of all the elements in this array, right? We know its value, but then, because we have we have gone out of values for j for this specific I, we are going to exit the loop and go again in the loop. And now I gets increased. So I will become 1, right? Awesome. And then when I becomes 1, we enter again the second loop. And what's the first value that j is gonna take? Well, its first value is going to be I, always, right? So we start from here, right? So my point is, from the whole array, which was the previous subarray that we knew the sum for, the new array that we take into account is only this one, only 2, right? So we also have to take into consideration these scenarios. And doing that is actually pretty simple. When we finish this for loop, we know that basically we are starting again from the bottom, right? So it doesn't matter which elements we had in the previous subarray. We are starting with a new subarray because we have a new left point, right? We are starting a new subarray from index I, and we also know that the first j for that subarray will be also I, right? So what I can do here is that when I change the left endpoint or the I can initialize my sum with 0. And that's it, right? Think about it. Let's go again in that scenario. So I was here, right? J was here. The sum was, anyways, the sum of the whole array, doesn't matter. I finish this for loop, I go out of it, and now I know that it's the time to try out the subarrays which have the left endpoint at 1. So I enter again the first for loop with I equals 1. So I moves here. After I do that, I initialize the sum with 0. So no matter the sum, how much it was, it's now 0. And then what happens is that we enter the second for loop. The first value of j is I. So on this iteration, j becomes I. J is not here anymore. And the first thing that we do is increase the sum by nums of j. So from 0, the sum became nums of j, which is nums of I, because they are always equal at the first iteration here, which is 2, right? So these are the only two things that we need to do. When we are still inside this for loop, so we take an extra element, the next element into our current subarray, increase it to the sum, but when we basically reset that subarray and start again from the next left endpoint, we also reset the sum and for each j increase it again, right? So as you've seen, j is now 1, sum is 2. On the next iteration, j will be here, right, on index 2, and the sum will get increased by nums of j, which is 5. So the sum is 7, and so on and so forth. And then again, we move with I on the next one, and starting again with sum equals 0 and increasing, and so on and so forth. So this is a super smart and elegant way of knowing the sum of each subarray that we fix, right, from an array, only by having a variable, and of course, in constant time for each subarray. Why do I say that? Because, as you can see, the only thing that we do is either reset the sum to 0, either increase the sum by something, right? So no matter in what scenario we are making a constant operation to update our sum, which is amazing, right? Obviously, this is still a brute force approach, because the first part is the one that's really messy, because think about it, we are trying out each and every subarray. The second for loop, which how many iterations it does? It's n minus I, right? So this one does n minus I iterations, and those n minus I iterations happen each time we enter the first for loop with some value of I, do those iterations, move to the next value of I, do again those iterations, right? So when I is first equal to 0, we are making n iterations. Then when I is 1, n minus 1. When I is 2, n minus 2, and so on and so forth, until when I is equal to n minus 1, we do how many? 1, right? You know this sum, obviously, is the Gauss sum. We've talked about it. It's n crossed n plus 2 divided by 2. So, of course, the time complexity of this algorithm, I mean, I haven't written the part where if sum is greater than the answer, we update the answer, right? So that's obvious. Answer becomes max between answer and sum, and then return the answer. But you got the idea, the whole algorithm is big O of n squared. It's not good, but it's better than having nothing, right? This is the brute force approach of the problem. Longest subarray of some maximum s, right? Remember the trick with the variable, and let's see how we can improve this approach. All right, and here is the brute force algorithm that we've talked about. Now, as you can see, I am using two variables, answer left and answer right, to store the left and right endpoints of our answer subarray. I initialize them by -1. This is a way of saying that I didn't find any subarray of some maximum s by now, right? Because I haven't gone through any of them. Be very careful here, because I was also tempted to initialize them with 0, which is not a good idea. You know why? Because if you initialize them with 0, you suppose that the subarray 0, 0, which is consisting of the value nums of 0, is initially your solution. And that's not always right. Maybe this element is greater itself than the sum s. So if you do that, you are going to take it into account for the solution. And let's say, I don't know, we have the array 4, 5, 6, right? And s equals 3. In this scenario, we have no solution, right? And this is very important, because if we have no solution, but we initialize them by 0, we are always going to return 0, 0, as we won't find inside the algorithm any other subarray with a sum less than or equal to s. So, initialize them by -1, just to suppose that initially there's no solution, which is correct, and then go on and search for the subarrays. Awesome. So let me erase all of this. And after having these variables set to -1, I am trying out each index I from 0 to n-1, right? The left endpoint. I am initializing the sum by 0. I am trying out each index j for the right endpoint, right? And now inside I have the subarray ij. I update the sum to make sure that sum holds the real sum of this subarray. And then I check if this sum is less than or equal to s. So the subarray is a valid one. And here is very interesting. I have here parentheses. And I have two statements which are separated by the OR operator or word, right? What this means is that, first of all, I definitely need the sum to be less than or equal than s. And either I haven't found any solution by now, so n's left is -1, so this is the first valid subarray that I have encountered so far, or, and when I go to or, it means that n's left is different than -1, so I found at least a solution in the past. j minus I plus 1, which is the length of the current subarray, is greater than the length of the answer subarray for now, right? The current answer subarray, the best subarray that I've ever encountered. If this one is better than that one, so it has a greater length, then of course I will change my answer subarray to be the subarray ij. In the end, I return the pair n's left and n's right. Alright, I wanted to show you this because this is tricky with the initialization part, and make sure you always get it right. Because again, if I initialize them with 0, that would have been a problem. And also, if I didn't have this n's left equals -1 or, then I would have ignored the solutions of length 1. Again, let me show you an example because it's super important. Let's say I have the array 7 to 7, for example, right? And guess what? The sum is equal to 7, right? So initially, both of them are -1. I is 0, j is 0, the sum is 7, which is less than or equal than s. But if I didn't have this, I would have checked only if j minus I plus 1 is greater than n's right minus n's left plus 1, which doesn't happen because n's left and n's right are both -1. So n's right minus n's left plus 1 is also 1. 1 is not greater than 1, so I wouldn't update my answer. And this happens for this subarray, and also for this subarray. So when I have valid subarrays of length 1, if I don't check if n's left equals -1, they won't replace the initial -1 solution, and we are going to return it in the end. But -1 means that no solution exists at all, and we shouldn't return something like that when we have in fact solutions, right? So again, very tricky, but be careful with initialization and checking then, based on the initialization you just made, if we have encountered a solution, and make sure that the real solutions will actually replace the fake one, quote unquote, from the start, right? Again, this algorithm is a big O of n squared, is a brute force approach, but it's a very good starting point, and we will see that one simple mathematical observation will make this algorithm into a big O of n. And that's for the next lesson. See you there, guys.